and action. You don't,
I say
you
action.
don't say action.
I say action. And action.
Damn it. You got to get one of those. I'll get you one of those clap. Scene
Scene
once, take 87. I'm not doing. I did 187. All right, now we're ready. So I'm going to do substitution rule right now. But I was tangented because I was watching. I don't know who it was. Should I say? Covering your mouth doesn't negate the saying it out loud. I was watching MIT, and they were talking about this guy. So I didn't see the previous video when he did the limit of it, etc. But I just wanted to give a quick idea of. Let me wind it back and start with this. And now that you've seen it, either skip ahead and don't look at what I erased. I already watched and saw on the screen. You probably didn't know it was all Greek to you, anyways. So before I do substitution rule, he called AK. It's like there's the joke. Motherfucking AK. Picture, I said. All right. So I've got the sequence AK. I also don't like K, so I'm going to use N because they can do whatever you want unless you're the grader at the U of A, and then you better use a K. So I've got this guy AN, and we want to know as n tends towards infinity. So I'm going to start drawing it already. We're going to draw on a graph, and the sequence. You don't do this a lot when you do sequences. A sequence is a list of numbers. It turns out that the first number in here, you can't put 0 in there, but I can put A1 in there. I can do A1 half, which is the square root of 3, which is 1.73 approximately. A1 is 1 plus 1 to the 2, which is, or sorry, to the 1, calm down, which is 2. So it's 2, and it seems like when you phrase it this way, everyone wants to say as this is where n is going to go to infinity, and then this is an. And I want to know what happens to this sequence, this list of numbers. Does it converge to a value? Does it just keep growing indefinitely, unbounded? Or when we start looking at sums of sequences, then this is going to be power series representation. A power series representation is the limit of your partial sums. So we want to know whether these converge or diverge. And in particular, if it does converge to a number, where does this go? And everyone wants this to go to 1. Because we say in general, if I have a limit as n approaches infinity of n squared plus 2n plus 7 over n squared 3n squared plus 2, where does this go? 1/3. Why? Because the dirty trick is you can do it like this. I don't like to do this, but 1 over n squared over 1 over n squared. I don't want to. So what I do is I see the dirtier trick, and I want to take n squared out of that. This is more useful in more than one application. So if I take those things and I wanted n squared out of each term, then I have 2n, so I have to multiply by n over n. And then plus the 7 has to have n squared, so I multiply by n squared over n squared. So my mantra is take out the highest power because they're going to make them algebraically a little bit more complicated. Limits at infinity when n or x goes to infinity, take out the highest power of n on the top and the bottom separately, and then see where that goes. The trick of that is because all the 1 over n functions go to infinity regardless, or go to 0 at infinity regardless of what type of 1 over n to the k it is. So all these guys go to 0 at infinity. So the trick is take them out and then see what happens. If this guy on the top is larger, it'll go to infinity. If the guy on the bottom is larger, it'll go to 0. If they're equal, squared, it'll go to the leading coefficient over leading coefficient, so I can see it 1/3. There's the limit. Why? Because I'm doing that. Now, that'll have to do with this in a second. Now that I do that, this one had plus 2. So what am I missing? N squared over n squared again. So I'm going to take out n squared on the top and the bottom because it happens to be the same. It's going to converge to the finite number. This is like a Riemann sum, the area under x squared plus 1. No. It's 4/3. We only got 1/3. Close enough. Yeah, it's 1/3. Something like that. These are Riemann sum limits also is what I'm saying. So now that I do that, I get equals the limit as n approaches infinity of n squared 1 plus 2 over n plus 7 over n squared over n squared 3 plus 2 over n squared. Hit the TV. Now where does that go? Now because it was equal, it goes to this, and the whole point was I just said this, all of these go to 0, 0, 0. So this goes to 1/3. So my point being is the trick for limits at infinity is to pull out the highest power of n, and sometimes when you have a conjugate, conjugate it first and then take out the highest power of n. And then I'm using the fact that these guys all go to 0 at infinity. So now that was the point of that was, yes, 1 over n, even though he's discrete, or 1 over x, is this guy. At infinity or negative infinity, he does go to 0. If you're not looking at, when you look at limits, if you're not looking at the behavior of a sequence or a function at a value, you're not doing them right. Because this is saying ak, or an in our case, is going to go to 0, and it's 0. So this, you want to go to 0 is my point, long story short. You want that to go to 0, and then you say 1 plus 0 to the n goes to 1 to the n. But that's, no. So first of all, let me make that look a lot scarier so that you see that that's probably not where it's going to go. Also, before, when I make it look scary, you should have used the brute force. List some of them for yourself and see where it starts going. So I'll do that first. You want scary, or you want baby bear or papa bear first? No one's here and I'm by myself, so it's like there's nobody even here. So I'll drive, but let's look at what happens first before we do this. So I need 3, 2, 1, 1, 2, 3, 4. So a1 is 1 plus 1 over 1 to the 1, which is 2 to the 1, which is 2. A2 is equal to every time this is n plus 1 over n. This will also be good when I do the limit. You're like, you said you were going to be quick with these. I start talking about math, and here we go. So this is always going to be, when you do 2, it's going to be 3 over 2 to the 2, which is 9 over 4, which is 2.25. It's getting slightly larger. Does it go to infinity, or does it cap off? And this is what we want to know. And one way to do this is to just compute the limit using L'Hopital straight out, or show that it's monotonically increasing, bounded above by 3 using induction, and then therefore by the monotone convergence theorem, you have convergence of this to some number. What is that number? It's getting larger and larger. A3 is going to be 4 over 3 to the 3, which is 64 over 27, which is 2 point, I don't remember, 370, something like that. Correct me in the comments. I don't care. I'm not going to read them. A4 is going to be 5 over 4, which is 5 to the 4 over 4 to the 4. See how I'm writing it like that? Watch what's going to happen again when I do it with this. It's not going to 1, everybody. Not going to, 1's way over here. And we started at 2 and are going up. And where are we going? E is what's going to happen. E. So what is this? 625 over 256. I don't know what that one is. Decimal. How do we do that? This better be what? It better be a 2. And then you'll get the decimal expansion. You do it. My point being is, it looks like we're going up, but then you can show, using what I was just saying, that this is monotonically increasing and bounded above by 3 even. You can cap it at 3. It's not the supremum, but it's cap it at 3. E will be the limit of this, actually. And then what we're going to get is that this does converge, and it converges to E, but you think it goes to 1. So why do you make this mistake? So first of all, let's use a little bit of basic algebra to make this look a lot scarier. AK, motherfucking AK. Might as well keep it AK. What I want an N, then I can't use the joke. Look it up, and then I'll never use it again. So AK is 1 plus 1 over K to the K. And you're like, 0, then 1. No, write this the other way. I did it with the 5. This is 4 plus 1 to the 4 over 4 to the 4 is 5 to the 4 over 4 to the 4. Now do you see that what I'm seeing? Oh, it's that looks horrible. That's definitely not going to 1. 1's way the frick over here. Or, well, Wait a frickle. That is 1 also. I was correct. But the wrong axis. So what's happening here is this is definitely how are we going to deal with this. And then this is where I started watching the MIT video. He said he did this limit last time, but then he said he didn't do the steps or explain it very well. So I'm going to, I guess. We'll see if you like it better. So there's the scary, that was the baby bear, and then there's the polar bear. Now I'm convinced it's not going to 1, that's for sure, wherever it's going. And I do know I cheated, that it is bounded above by 3 and is monotonically increasing, which means AK is less than AK plus 1. And it's AK is less than 3 for every K greater than or equal to 1. So then the monotone convergence says it does converge. The limit as n K approaches infinity of AK equals L. Let's find L. And then we'll do substitution rule. All right, we will do that in a second. We're still, it says substitution rule, and all I did was L'Hopital's rule on a sequence and showed it was E. While I was watching an MIT video waiting for the cameraman to edit my videos faster. Look how fast I am. It's not the same. It's not the same job. So now what is this? The limit as K approaches infinity of AK. What we want to do is the same as logarithmic differentiation. I want to log both sides. Log, so I'm going to call, or log of AK is going to be log of 1 plus 1 over K to the K, which is exponent on the inside becomes number on the outside, which becomes K times the log of 1 plus 1 over K. And this is the point at the video where he said it's balanced out, because this is going to go at, now as K goes to infinity, where is this going? He's going to go to, I hope K goes to infinity as K goes to infinity. And then, yes, you are correct when you were earlier assessing. Now, log is continuous, so I can interchange that. And then this limit is going to go to 1. Log of 1 is 0. So you were correct. But now this is 0 times infinity type, which is L'Hopital's, which he didn't say. It's not L'Hopital, it's Bernoulli, but okay. And then what we want is, and he said it balances out, and then we have to find out where it balances out to. I call it a tug of war. This one's trying to tug to infinity, and this one's trying to tug to 0, and I want to know where it goes. And then it does balance out, I guess. He's correct. He's from MIT. Screw you. But okay, yes, we want to know which one wins, or whether it does balance out, and definitely doesn't balance out at 1. It balances out at 2.718281828, something, something, something. Right shoe. Get the picture. Okay, so where does it go? Now that I've done that trick, this is exactly what I'm going to do. This says that I want this, so keep that there actually. But now what we're going to do is, let's call y equal AK, which is 1 plus 1 over K to the K. Then we have that the limit as K approaches infinity of y is equal to this, is equal to the limit as K approaches infinity of AK, which is the limit as K approaches infinity of 1 plus 1 over K to the K, which is what? No, I wrote that wrong. Yes, that's right, but the whole point was now what I'm going to do is log y both sides. I'm keeping that in. This is what? K ln 1 plus 1 over K. Also, I need differentiation, so BT dubs, you should know what differentiation is by now. So I'm going to use two avatars, K plus 1 over K equals 1 plus 1 over K. When I take the derivative, I want to use both of those to work smart, not hard. Change it into something using a little bit of algebra, which you're all scared of, and it'll make this differentiation horrible nightmare that he was talking about in the MIT video a whole lot friggin' tricky. I'm going to get dirty tricks. Dirty tricks. So I'm going to use that in a second. Now, the limit of log y is equal to, and I have to interchange this. Log is continuous. I can write this as log of limit as K approaches infinity of y, which is this. I want to know what that is, but we did this clever trick. So we did this at the end, and by the time you get there, 4 is for the trees. You don't remember that this is what I'm going to apply this at the end. So there, first. Where are we going? I don't know, just start shooting. You're not hunting, you're Pray and pray. So now the limit as k approaches infinity of ln y is equal to the limit as k approaches infinity of, now correctly, k times ln 1 plus 1 over k, which is infinity times 0 type. Now what I can do with this, watch my L'Hopital videos, but we can take this now and I can write what that says is this function goes to 0, so 1 over it will go to infinity. This function goes to infinity, so 1 over k goes to 0. We just went over that. So I can do either one. Which one do you want to do 1 over 1 over? And also k is equal to 1 over k. Do you want to do that, or do you want to write log 1 plus 1 over k equals 1 over 1 and then take the derivative? Not even a chance. So when you're asking 0 over 0 type is infinity over infinity type or 0 over 0 type, because I have both actually, but then you're like, which one do I pick? So now there's choice, and we don't want that in math. Here's how I rectify that for myself. Which function is good when I do 1 over 1 over, which one's easier to take the derivative of? Not this hot mess. So that's what I'm going to do, which gives me now what? All I did was take this k. Mark Solomonovich did it for me, and he didn't point this out, and he's like, what did you do? You did some magic happened right there. What happened? And then now I'm going to do this for a second, because that's the same thing, and this becomes 1 over k. Yes. Now this is what? 0 over 0 type. That e was trying to get away from me. E is where we're going specifically. So now, by L'Hopital's rule, which is Bernoulli's rule, shout out Bernoulli. We gotta get paid though. Poor mathematicians. He sold his soul too. So will I. Just like Bernoulli. Okay, by the Bernoulli rule, we have that this is the limit as k approaches infinity of the derivative of the top and the derivative of the bottom. So 1 over the derivative of log is 1 over the inside, which is written this way, k over k plus 1 times the derivative of the inside, which is easier to take in that avatar, which is what? If you know what you're doing like a wizard does, that makes that MIT calculation a whole lot fucking easier. Now where does this go? Oh, step 1, polynomial, take out the highest degree on the top. This goes to the limit as k approaches infinity of k over k plus 1, which is what? K times 1 over k times 1 over 1 plus k. Cancel, cancel. 0, this goes to 1. But careful, that's not where we're going. You're like, you just said it didn't go to... No, it didn't. Log y went to 1. Log y. I want a mog y now when I say log y's. Log y! He's like, yeah. You say a lot of things. Shh, I'm the king of France. Now that says that... Which way do I want it? Yes. The natural log of the limit as k approaches infinity of ak, I'm serious when I lean like this, I'm on the home stretch, don't cut yet, is equal to, interchange those because of continuity in reverse, I'm now going this way, do you see? The problem with life is you're doomed to live it forwards and only understand it backwards. So there you go, I wrote it forwards first, now I'm applying it backwards. This guy is equal to, what? We just found a limit. The natural log of, this limit was equal to 1. L is what I called it. Do you see why I did that? Now, and I get the limit as k approaches infinity. What was ak? 1 plus 1 over k to the k is equal to E. Our friend from Leonard Euler. There's a video that I was supposed to be doing substitution rule. There's a video on L'Hopital's rule and the number E using a sequence instead of a continuous function, whatever, close enough. All right, we're just gonna go straight into grandpa bear, screw baby bear, mama bear, papa bear. Out of context, that's not what I meant. So if we have the integral of a function which has some more complicated, that's usually why if you have a square root or something, that's probably, the inside of that is probably your substitution. So there's the f. And then what I also need is a differential. I'm going to call that dw. Why? dw is f prime of x dx by differentials. So we're going to use differentials, and then we have a thing, it is, you can use substitution rule. And so let's use substitution rule at least once. I want that twice, it looks like possible. Oh, there's going to be another one. I won't even turn the page. Turn the page. So this is the integral of, holy crap. Oh, I've got a dx. It can. It didn't have to please me, but it did. So, how are we going to do this? All of a sudden, yeah, it's like we forget. I just used. I'm going to use that, but holy crap, you need to see that. We're going to need to see it more than once. It's going to happen 3 times in a row, I think, here. And you have to know a bunch of, I'm assuming, at some point when we're doing integration, you have to have a Rolodex. We're going to go through that Rolodex. Algebra, lexicon, substitution rule, trigonometric substitution, all these different types of things. What can I get rid of? So what you're looking for horribly is a function and its derivative, possibly up to where now this one has done. This one's a red flag. But so we're going to deal with him in a second. You're like, that's what would fuck with me. If it wasn't there, pretend he's not there right now. Then do you see a little bit more what I might call my thing? It's like, I still don't really know. It's like, okay, well, maybe what if I, so first my brain is seeing that. I want that to be dw. So I'm working in reverse a little bit. But you're like, I don't see the derivative of that guy's not going to be. No. But if I get rid of this, using my old friend, the Pythagorean identity, now we're in business up to a constant. Did I do it right? If I do that now, as I did that even, I'm cheating. It's like, you're cheating, stop cheating. As I did that, I think we're going to get slightly, oh yeah, my finger makes a noise too. See what happened? What I just noticed? I think this is going to be the entire differential. Either I made a mistake or... Oh, I see. We could do both, I think. Rein it in. It's the curse of knowledge. I've already looked at it, and then it's like now, as I'm doing it in real time, I disagree with old AJ wrote fucking something down, and now current AJ wants to change it. Who's AJ? Stage AJ. So, first let's make that move. So I'm going to change this. This is equal to, I'm going to go up here because I'm going to run out of room. The integral of sine x cos x dx over the square root of, I want to factor that in right now. So I get a squared minus b squared sine squared x plus b squared. Now that helps make me see with old AJ. He's all right too. Currently I'm old AJ, and old AJ was past AJ was young AJ. All of them are me. So this I'm going to, and then yes, that won't be part of it. I'm going to let W equal sine x. Then w squared is sine squared x, that guy, all x's must go, and dw is cos x dx. But then you're like, well, what is that? Well, sine is w, so I'm going to put it there, and then I have another substitution, and that's why I was saying he was just listening to me muse over it. I was like, I didn't even see the square root at first. It was like, man, that's going to be a third substitution, so just hang on. So now you see where it's going. One substitution is going to make now an algebraic in W substitution, which I can still get because I have the it's creating the differential for me for the next substitution, and then the square root got me, and it's like, oh, there's a third one. Can you see them? Can you see what I see? No, you can't. You're not a wizard yet. I'm just making a song for you. That's open. That's like an old religious Christmas song I was just humming. We can steal that at will. Or you don't have to give any credit. H bomber guy. So this is equal to the integral of w dw over the square root of a squared minus b squared w squared plus b squared. Now that frickin' junk is going to become my differential, and I'm not using u. I don't care about the other books. U and dv are strictly in my brain reserved for integration by parts, which will be the next technique. Dt now is going to be a squared minus b squared w squared plus b squared, the whole thing. And I'm also going to rewrite that in a second, right now. And then they do that to you too. You can move him, it's okay. There you go. They're commutative, they were all numbers. They're horrible numbers, but they were all numbers. What was that? There. Now I'm seeing that that's just going to be a negative 1/2. So what does this become? This equals, by my substitution, I was getting ahead of myself. Whoa, how come I got a dt of a dt? How do you do dt of a dt? That's the second one. Sadness remains. Dt is equal to what? 2a squared minus b squared w dw. W dw, George W. I don't know why I was looking over there to put it down. So now with this substitution, I get equals, what do we get? Disembodied voice. We get integral of t to the negative 1/2 a does not equal b, so a squared does not equal b squared. Clearly I said that. If they were equal, it would have been a much easier identity. So they're not equal. So I can, why did I just do that? Because Mark will get me otherwise with his lightning bolts. I'm trying to divide. So I looked at this and I said, I don't have that exactly. So that is equal to 1 over 2a squared minus b squared dt. I moved it over. Because I didn't have this. So that's equal to 1 over 2a squared minus b squared dt. Now what is this? This is equal to 1 over 2 times 1 over a squared minus b squared times the integral. No, I can just do it, can't I? Yes, the antiderivative of this is now what? The power rule. It all came down to doing that power rule, which is now what? Well, I guess I can do it. 1 over 1 plus negative 1/2 t to the negative half plus 1 plus c, which is equal to 1 over 2a squared minus b squared times, what do we get? 2 root t plus c. We're not done yet. What was t? T was this. I'll just do it right here. A squared minus b squared. What was w? Sine, I left it. They want it in the original variable that you got it from, so there you go. That's how you do substitution rule. 3 times. 2 times, math is hard.